Topic 2.8, Centripetal Acceleration. Our goal with this topic is to ultimately be able to explain phenomena such as the demonstration that I'm about to show. By understanding centripetal acceleration, we'll ultimately be able to understand why, when I spin the plate around with a small cup of water in the center, the water stays inside the cup and the cup does not fall off the plate.
Can you come down a little bit? We'll have to like
See how that looks.
So if we remember correctly, the acceleration is defined as the change in velocity over the change in time. And acceleration is caused by forces. But the thing that we need to remember about acceleration is that acceleration has two components. That change in velocity has two parts. There's first of all the magnitude. And we've already looked at the magnitude. And secondly, it has direction. So centripetal acceleration So acceleration is said to occur when either the magnitude of the velocity or its direction or both change. Now, in the past, we've only looked at the magnitude of the velocity. We didn't allow the direction of the velocity to change. And that's what we're going to look at a little bit differently now, because now we'll keep the magnitude the same, but we'll allow the direction to change, and as a result of that, we'll find that we get a new kind of acceleration called centripetal acceleration. So the definition of centripetal acceleration is the following. And you've felt this centripetal acceleration in many situations. When you go in a roller coaster and we go through a loop, we feel the centripetal acceleration. When you go around a turn in a car and you feel that force that makes you feels like you're being thrown to the side, that's also that centripetal acceleration. Now, to understand centripetal acceleration, we need to look closely at what is the direction of the velocity as our path changes. So we'll draw an example path. We'll put a nice curve to the path. So this is our path. And we can look at the velocity at several points. So let's pick a couple of points. Okay, at this instant in time, at point A, the direction of the velocity is always tangent to the path. That means to say that it's parallel to the path. So if I were to draw the velocity vector at this point, the velocity vector would look something like this. This would be the velocity at point A. At point B, the velocity has changed directions. Our path has curved. And the velocity vector at this point, I draw the same length arrow. No change in the magnitude, but the direction has changed. And then finally down here at C, I get the velocity of C. So at each of the 3 points, I find that the magnitude of the velocity is always tangent to the path. So if I follow and I think of the direction of the velocity at any instant in time, then I find that that velocity always points along a direction that is tangent to the path, unless the path is straight. Now when the path becomes straight, the velocity and the path match up and point in the same direction. So let's look at a second example. This time, let's not just make a curved path, let's actually make a circular path. And we'll pick 2 points again, point A and point B. So again, at point A, we would find a velocity which points tangent to the path. So at this point, the velocity is pointing upward, but then later at point B, the velocity is pointing towards the left. And once again, the circle represents the path. So we should make a note here . Let's change this a little bit. Let's say the velocity vector, if we really want to emphasize the direction, is always tangent to the path. So the velocity vector is always tangent to the path, but to understand the acceleration of this object, we need to understand the change in velocity. So we need to figure out what is the actual direction of the change in the velocity.